Hello, this is video 43. We're going to talk about conservation of energy. So this is going to be a major topic for this course. So let's see the law of conservation of energy. So it says energy cannot be created or destroyed. It may be transformed from one form into another, but the total amount of energy never changes. So maybe you've heard this before, energy cannot be created or destroyed. That is the premise here. So this picture I have on the right hand side here, it just shows somebody that is falling out of a building here because there's a fire, and that person has potential energy due to her height above the ground, and she could have kinetic energy if she was in motion. She's not moving here, so she has no kinetic energy, but she has potential energy. Now as she falls, what you notice is that the total amount of energy does not change. She has, let's see, 10,000 joules of energy if you add them up the whole time. The only thing that happens is that her potential energy is going down. You can see she has 10,000 joules and then she goes down to 7,500 joules, 5,000 joules when she's in the middle, and then she keeps going down all the way to 0 when she reaches the ground. And her kinetic energy increases from 0 because she's at rest to 5,000 joules in the middle, all the way up to 10,000 joules. So the point is that her energy is transferred from potential to kinetic, but the total amount doesn't change. So what we have here is the equation that we're going to use. So if there's no if there's no non-conservative forces, then we say mechanical energy is conserved. Mechanical energy, by definition, is just the sum of all the kinetic and potential energies of the object. So if that doesn't change, that means the initial energy equals the final energy. You don't lose or gain energy. Now the initial and the final simply refer to whatever two parts of the problem that you're talking about. So if you're looking at her motion from the top to the bottom, then the top would be the initial, the bottom would be the final. But you could look at her motion, what about from when she goes here to here, right? From 1 to 2, then 1 would be the initial and 2 would be the final. So that's what initial and final means, just the 2 points that you're looking at, where the person is starting and where she is ending. So we have only talked about one type of kinetic energy, the regular kinetic energy 1/2 mv squared. And then we've talked about two types of potential energies, the gravitational potential mgy and the spring potential energy 1/2 kx squared. So that's why both of these are added, both of these are potential energies. And I've used the 0 subscript to represent initial. So I could have written 0 here, doesn't matter, I or 0. And then I've rewritten all of those three types of energies with a F subscript to represent the final quantities. So this is the equation that we're going to learn how to use in this video. But I really recommend that you pause the video for a minute and watch this YouTube video. It takes just about 2 minutes. It's a really great demo. It's very entertaining. I really recommend it. It's some guy, he has this bowling ball or some kind of wrecker ball that he's right there and he lets it swing, and it could potentially hit him in his face here as he lets it swing. So he's risking his life to do this video. So take a second to watch it. It's really good. So let's take a look first at a conceptual question here. So it says a block is released from rest on a frictionless incline as shown. When the block is in contact with a spring and compressing it, what happens to the gravitational potential energy Pe sub g and the elastic potential energy Pe sub s? So you can see, and the mass and all these distances don't really matter. I just wanted a picture here. We have a mass that's on this incline, and as it falls down, it's compressing the spring. So you have to think, what happens to the potential energy, the gravitational one? Well, that one is defined as mgy. It depends on the height. The height is decreasing. So that means that the potential energy, gravitational, is decreasing. So we can cross out choice A and cross out choice C. And then what happens to the spring potential energy? Well, the spring potential energy, PES, was defined as 1/2 kx squared. So we said when your spring is stretched or compressed, that's when it's storing this type of energy. So as it's being compressed, that means you have some X, you have some compression, so you have energy. So as it's being compressed, that energy is actually increasing. Because when it's not compressed right here, that's when it doesn't store any energy. So the answer is choice D. The gravitational potential energy is being converted to spring potential energy. So the way that we're going to solve conservation of energy problems is when we have a problem, first of all, how do we know if it's a conservation of energy problem that we're dealing with? So the way I like to think about it is you have to think to yourself, is my object losing height or gaining height? Is my object speeding up? Does it gain velocity? Or does it slow down? Does it lose velocity? Does v become smaller? So if you notice that the height is changing and or the speed is changing and or a spring is being stretched or compressed, then when at least two of these things are happening, then you have a 99% chance this is going to be a conservation of energy problem, because it means that energy is being converted from one to another. If your height is dropping here, if you're losing potential energy, then you must be gaining another type of energy. So that's kind of how you know that it's a conservation of energy problem. Now, once you realize that, then the way that you solve it is you identify the zero level and the givens, right? So if your object is changing height, you've got to define, okay, let's let my y equals 0 equal to that lowest point that we care about in the problem. Write down all the other givens. Write down the full conservation of energy equation. As you get used to this, you won't have to write down every term, but I really recommend starting out with every term. So then you cross out the terms equal to 0. So let's say the problem is simply an object that's falling down, so it's gaining speed. There's no spring in the problem. Well, then you would cross out this, because you say, okay, well, that's a spring potential energy, PES. If there's no spring, I don't care about that term, I can cross it out. If something is equal to 0, like the height, then you can cross out that term. So you're just going to cross out whatever is equal to 0, and then you can solve for the unknown. So I'll stop this video here and do part B in the next video where we can see an example.